Hey guys, we want to do a quick overview of asset-based balance so you understand what we can ask in an exam and how we can very quickly determine the asset-based disturbance in a patient. Okay, so the first thing is there's obviously a theory component to this. The idea that we're producing and eliminating throughout our day different amounts of water but also hydrogen and other things. So we want to maintain a balance. And the balance is trying to maintain a pH that should be between 7.35 and 7.45. We usually use the number 7.4. And we maintain this through different mechanisms. So obviously, if I look at the picture to the left, we see that throughout our day, we're going to degrade proteins, carbohydrates, and fats, which can either give us CO2 and water, or different organic compounds which form acids. These acids like sulfate, phosphate, urea, uric oxalate, acetate with the hydrogen are what we call non-volatile or non-fixed or fixed acids. And so the fixed acid will be secreted or taking the hydrogen, and we've eliminated the hydrogen throughout the urine. So we're eliminating the hydrogen as hydrogen. In the case of the breakdown products of all my organic compounds, obviously the carbon will be released as CO2. But that CO2 to be transported into the lungs, it has to be by carbon and hydrogen, which by carbon will be transported in the bloodstream. And when I reach the lung capillary, we convert this back to CO2, which can be excreted in the atmosphere through exhalation. So this is what we call non-fixed or volatile acid. So if we look at the image towards the right, the non-volatile acid increase. This can be, in this case, buffered by bicarbonate to form, again, like I said, CO2 and water thanks to carbonic anhydrase. As this is happening, we know that the bicarbonate, because there's more acid, will be used to not permit pH to fall as much. But eventually, all of that will be tried to be eliminated as water and CO2. And as when we have a volatile acid increase, like CO2, CO2 will combine with water to form hydrogen bicarbonate, and this can be done thanks to carbonic anhydrase. The idea is that we need to remember that CO2 and water can become carbonic acid thanks to carbonic anhydrase, and this becomes hydrogen and bicarbonate by dissociation. And it's the opposite. If I have more hydrogen, hydrogen and bicarbonate become carbonic acid, which can be converted to CO2 and water thanks to carbonic anhydrase. So in this formula or this reaction, it can go either to the right or to the left. I can take CO2 and convert it to hydrogen, either if I have too much CO2 or too little hydrogen. Or I can convert hydrogen to CO2, I have either too much hydrogen or too little CO2. Okay. So we're going to use basically this formula in a second, or this graph with just Davenport's the diagram. And we can see here that the idea is that we have in the x-axis pH, and we know that 7.4 should be the normal value of pH. Then we have in the y-axis plasma bicarbonate, and it should be somewhere around here, which should be 24. So plasma bicarbonate should be 24. And the joining of these together should give me a curve, which is going to be, this curve is going to be for a partial pressure of CO2 of 40. Now I can, and this will happen in the exam, I will put, if I put a curve that's to the left or closer to the y-axis, it's going to be a higher PCO2, 60, 50, whatever. If I put a curve that's going to be farther away, it's going to be a PCO2 of 20 or less than 40. And here you can see how in normal circumstances, if I take a blood sample and I measure everything that's positive and subtract it with everything that's negative, the value should be 0. But because we have to spend money to make these lab values, we only take specific compounds that are more important for us. In this case, we take the most important positive things that we take in blood will be sodium, and the most important things that we take out and that are negative are going to be chloride and bicarbonate. So we have a gap between them, which are all the other proteins and organic acid that we're now calculating that are negative. So this difference between sodium and chloride is going to be the gap junction. There will be the gap junction or anion gap, And this anion gap can increase in some metabolic acidosis, only that condition, when we're losing bicarbonate but gaining a new acid, a new compound, organic anion that will increase the acid. Okay. So a couple of things. One of the examples of metabolic acidosis, we'll talk about this. We have a normal anion gap, will be renal tubular acidosis. In the case of renal tubular acidosis, we have three types that we're interested in. Type 1 is something that's happening, or a change in the distal tubule, where we have an impaired hydrogen secretion, specifically by the intricate cells. Urine pH will be high, plasma bicarbonate will be variable. So the defect here is the decrease in the hydrogen potassium ATPase activity. So we can basically have a backflow of hydrogen and less sodium reabsorption. Then we have a secondary, or type 2 renal tubular acidosis. Here this is happening in the proximal tubule. Here I have a problem reabsorbing bicarbonate. The urine pH will be variable and bicarbonate will be low. So this is a non-specific tubular dysfunction, and that's basically it. And finally, we have hypoaldosteronism, so too little aldosterone. The patient will basically have a pH that is low. Plasma bicarbonate can be a bit higher than normal, but still low. And we have hyperkalemia because we're not secreting potassium. We also have an acidosis because we're not secreting hydrogen. So the effect here is an impaired sodium reabsorption by the epithelial sodium channels, or NAD channels. So Addison's disease could be an example of this. So the ways we maintain the pH in a patient should be either this. I'm going to go through fastest and to slowest. The fastest is through buffering systems, either the carbonic acid bicarbonate mechanism, phosphoric acid phosphate mechanism, or proteins. This is very fast, but saturates very quickly, so this is not very helpful in the long term. The second mechanisms to maintain pH balance should be between the respiratory system. If I hyperventilate, I take an excess CO2 out of my body, so that means I can eliminate the acid as CO2. If I have an alkalosis and I want to increase acid, I can hypoventilate, so the increase in CO2 can form more hydrogen. That's the second mechanism. And the third mechanism, and this is going to be working in minutes, 2 hours, and it's pretty fast, and it tends to work specifically when I have a metabolic acid-base disturbance. And finally, I have a mechanism, which is the renal system. And the renal system is very good because even though it takes hours to days to work, it's very effective in controlling my acid-base disturbances. So if an acidosis, the way that the kidney manages this process is either or increase bicarbonate reabsorption, like we see in the image here in the proximal tubule. The CO2 and water is going to form hydrogen and bicarbonate. Hydrogen will be excreted or secreted into the lumen thanks to a hydrogen-sodium exchanger. The hydrogen will bind to the bicarbonate that's been filtered out from blood into the lumen. This forms carbonic acid, and thanks to carbonic anhydrase that forms CO2 and water, which can go into the cell, and then again carbonic acid forms carbonic acid. Carbonic anhydrase forms carbonic acid, which starts the process all over again. So all the filtered bicarbonate should be reabsorbed, or 90% of it should be reabsorbed in the proximal tubule. So one way is through reabsorption of bicarbonate. Another way should be by forming new bicarbonate, which happens usually in the distal tubule. And finally, obviously, with the secretion and excretion of hydrogen. Here we can see how we can form new bicarbonate in alpha intercalated cells. Again, we have a CO2 and water, and thanks to carbonic anhydrase, they form carbonic acid, which dissociates into hydrogen and bicarbonate. And the hydrogen now can be taken towards the lumen either through a hydrogen ATPase pump or a hydrogen potassium exchanger. That's why intercalated cells not only secrete hydrogen, but it can reabsorb potassium. But now the hydrogen needs to be buffered, and I cannot buffer it to bicarbonate because there shouldn't be any more bicarbonate left. So the best way I can do it is to use another type of buffering system, which in this case is phosphate. So hydrogen plus phosphate forms phosphoric acid, which can be eliminated in urine without changing too much the pH of urine. And there's another way. So I'm secreting hydrogen and forming new bicarbonate. In the proximal tubule, I can also form new bicarbonate, but by using glutamine, which either forms alpha ketoglycerate, which eventually forms bicarbonate, which can be taken into blood, and the NH3 can either be pumped out of the cell, or I can bind it to hydrogen to form NH4, which can be counter-transported with sodium. Another way that we can have to form new bicarbonate and secreting hydrogen is in the alpha intercalated cells. CO2 and water again will form hydrogen and bicarbonate. Bicarbonate is new, so I can take it into blood. And the hydrogen again, through either a hydrogen pump or hydrogen potassium ATPase pump, will go into lumen. Here, NH3 from the interstitium of the medulla will diffuse through the paracellular pathway, and it will bind to the hydrogen to form NH4. Again, to not lower too much the pH of the patient. We already talked about what happens with hypoamiding, so I'm not going to repeat it. And the idea now is we're going to take, I'm going to stop here, and we're going to continue on and explain the 6 acid-base disturbances, which are going to be respiratory and metabolic acidosis, respiratory and metabolic alkalosis, and mixed acidosis and alkalosis. So I usually always forget to change this, but remember the pH should be 7.4. Lower than this is an acidosis, doesn't matter what else. Higher than this, it should be an alkalosis. Obviously, I'm talking in ranges, so 7.38 is not an acidosis, and 7.41 is not an alkalosis. You know the ranges, but just to remember a simple number, we're going to use 7.4. The partial pressure of CO2 should be 40. If I had too much CO2, that means I'm forming more acid. So 40, 55, or 60, that means more acid. Less than, that means I'm forming CO2 into something else, or I'm accumulating bicarbonate or less hydrogen. So 20, 15, 25, that means I have more an alkaline situation. And bicarbonate should be again a range, but we put the number 24. And if I have more than 24, that means I have something that's basic. If it's less than 24, that means it's something that is acid. So a couple of things. If the disturbance is a respiratory, because the respiratory system is going to be compensated by the kidney, that means it needs time to have an effect. So in respiratory acidosis, we need to find out if it's acute or non-compensated or chronic or compensated. In the case of metabolic acidosis and alkalosis, we don't need to do that. The only thing we may do is to try to just be aware if the respiratory compensation is correct. And finally, with mixed acidosis and alkalosis, we don't need to know anything else. As soon as we determine that it's a situation where we have 2 diseases or 2 disturbances, that person has both respiratory and metabolic acidosis, or respiratory and metabolic alkalosis, so it's mixed, we don't need to add anything else. Okay? And just be aware that in metabolic acidosis, I need to calculate the anion gap, which I said is sodium minus chloride plus bicarbonate, and this should give me more or less, it should be between 8 or 15 milliequivalents per liter. If the anion gap is increased, that means that the patient has a metabolic acidosis, which can be methanol poisoning, uremia, diabetic ketoacidosis, etc. If they have a normal anion gap, they could be hyperchloremia, it could be renal tubular acidosis, diarrhea, etc. So thank you guys, and we'll stop for a second.